The answers we're looking for tomorrow, they were actually written down decades ago.
So this is the big question we're going to tackle. We're going to dive into how a few brilliant, super minimalist ideas from the 70s and 80s didn't just build the internet we know, but they also handed us a blueprint for fixing the huge trust problems we're all facing right now.
All right, let's start at the very beginning. The internet's success wasn't some happy accident. The people who designed it had a really clear set of priorities, and right at the top of that list was one word: survivability. The whole goal was to build a network that could take a hit and keep on ticking, and that priority led to some pretty radical design choices. This right here is a killer insight from John Postel, one of the internet's key architects. Back in 1977, he basically said, hey, we're trying to make this one protocol, TCP, do way too much. It was handling reliable delivery and simple packet routing, and it was getting messy. His solution? Split them up. Create a super simple universal protocol just for routing, which we now call IP, and leave all the complicated reliability stuff up in TCP. And the result of that split is this elegant concept known as the Hourglass model. IP became the narrow waist of the internet. Think of it like a universal translator. It was a deliberately simple language that let any kind of network technology below it talk to any kind of application above it. The core of the network was, by design, kept stupid. And honestly, that was its superpower.
Now, this whole design was guided by a core philosophy, the end-to-end principle. The idea, as Salzer, Reed, and Clark laid out in their famous 1984 paper, is that the really important functions can only be done right by the applications at the endpoints. Pushing intelligence deep into the network itself just doesn't work that well. You have to put the smarts at the edges. And this leads us right to another powerful idea called fate sharing. Basically, the network itself doesn't keep track of connections. All that information, all that state is held by the devices at the end. So, as David Clark put it, if an endpoint goes down, its state goes down with it. Their fates are shared. This makes the network incredibly resilient because all the nodes in the middle are stateless. They can fail and the whole system doesn't come crashing down.
So we had this beautiful, resilient, end-to-end design. It was brilliant. But when it came time to build security for the modern web, we completely abandoned these first principles. We basically betrayed the blueprint.
Yeah, instead of keeping intelligence and control at the endpoints, we built this massive system of centralized trust. The entire security of the web, that little padlock you see in your browser, it all relies on a hierarchy of gatekeepers called certificate authorities, or CAs. We handed our trust over to them, creating huge single points of failure and just completely violating that end-to-end principle.
And just how big is this delegated trust? Well, your browser, right now, implicitly trusts over 100 different organizations to issue a valid certificate for any website on the internet. We're talking Google.com, your bank, everything. If just one of them gets compromised, the whole system is at risk. This is the exact opposite of that resilient, stateless network the original architects wanted.
And look, this isn't just some theoretical problem. In 2011, this centralized model failed, and it failed catastrophically. Let's just take a look at the DigiNotar breach, because it is the perfect, chilling example of what happens when this kind of delegated trust breaks.
It all started with that single point of failure we've been talking about. DigiNotar, a Dutch certificate authority, was hacked. An intruder got complete control over their servers, the very servers that issue these trusted certificates.
The damage was just immense. When investigators finally got in there, they found that at least 531 rogue certificates had been created for major domains. Just think about that for a second. Fake, but completely trusted, certificates for Google, for Yahoo, for Skype. They were all out there in the wild.
And the consequences were terrifyingly real. Those fraudulent certificates were used to launch massive man-in-the-middle attacks, basically intercepting the secure communications of over 300,000 users, most of whom were in Iran.
In the end, a Dutch member of parliament said it perfectly. This breach, a failure of a technical trust model, had put lives at risk. It's just this stark reminder that these architectural choices we make have very real, very human consequences. The decision to ditch the end-to-end principle created a vulnerability with actual life or death stakes.
So, how do we fix this? The answer isn't to invent some crazy new thing. It's actually to go back to those first principles. We need to rebuild the hourglass, but this time, build it for trust itself.
And this is exactly where a verification-first architecture comes into play. The core idea here is a direct echo of that original internet design. I mean, look at this comparison. This is the aha moment. Just like the original internet split the reliability part, TCP, from the simple delivery part, IP, a verification-first architecture, like the one Zenon is working on, does the exact same thing for trust. It separates verification, which is about correctness, from ordering, which is about simple consensus. It is the same beautiful logic, just applied to a new problem. And the parallels are just uncanny. The end-to-end principle is reborn as putting value at the endpoints. Fate sharing becomes local computation, where every node can figure out its own truth without a central authority. And that simple IP datagram, its echo is a minimal ordering layer, like a simple ticker tape that just provides a sequence, but doesn't tell you what it means. In the Zenon project, they call this momentum. So what's the new narrow waist of this cryptographic hourglass? Well, it's not a protocol for moving packets. It's a set of simple, mathematically provable tools, cryptographic primitives like hash functions, which give data a unique fingerprint, and digital signatures, which prove ownership. These become the new universal language that everything else can build on top of.
And what's amazing is that this design gives us these incredible properties that echo the original goals of the internet. Verification is bounded, which means it's guaranteed to work even on a low-power device. Refusal is a feature, not a bug. If a proof isn't there, the system just safely says, "I don't know," which is much better than making a bad guess. You can even do verification offline, making the system resilient to being disconnected, just like the original ARPANET was designed to be.
Okay, let's bring this all together. Why does this architectural deep dive actually matter to you and me? Because it represents a fundamental ground-up shift in how we establish trust online. Just look at these two models side by side. The current web security model delegates trust. It relies on social contracts with these CAs, and we just have to hope they don't get compromised. A verification-first model doesn't delegate anything. It relies on cryptographic proof, on raw math. There are no central points of failure to attack, and you verify things before you act, not after you find out there's been a breach. And this is the single most important takeaway from all of this. We can finally stop asking, who should I trust, and start asking, is this information verifiably correct? We can shift the very foundation of trust from people and organizations to pure verifiable mathematics. To bring it all full circle, let's go back one last time to David Clarke's 1988 paper. His words about fate sharing are just timeless. The same logic applies today. A system based on delegated trust, on replication, can only protect against a certain number of failures. But a system based on end-to-end cryptographic proof, that protects against any number of dishonest players in the middle.
And that leaves us with one final, pretty provocative question to chew on. If the correctness of data, of interactions, can be proven mathematically by anyone at any time, what role is even left for trust? It's a question that really suggests we are on the edge of a profound change in how our entire digital world is built.